we're going to go ahead and take this and flip it on its side. So we're going to be looking down this, we're going to be as if our eye is right here looking in this direction. So we're going to be looking right back along the x-axis. And let's see, nope, didn't work. So I don't know what I did wrong with my animation there. It looked good at one point. So this is what we're going to do. So for the moment, just look at this charge here, Q1 on the y-axis, and this one here on the negative y-axis, and we already know what's going to happen with that. The y components are going to cancel. That is, the components that are perpendicular to the x-axis are going to cancel, and along the x-axis, they're going to add. So if these are all Q1s now, so these are all identical charges. So the electric field on the x-axis is going to be 2 times what it would be for Q1. Well, we already know what that is. Matter of fact, let's do this again. We already know that this is the electric field for 1. So what's it going to be for 2 Qs? If 2 Q1s are equal, we know that they just add. So if Q1 equals Q2, to say it most clearly, this E1 and E2 is just going to be K 2 Q1 over R squared times cosine theta in the x hat direction. And this other component is going to, this y component, the component perpendicular to the x-axis, is going to cancel. Well, we also know that that's going to be true for this Q1 and this Q1, and this Q1 and this Q1. Don't know how that happened. Okay, we know that these pairs of Q1s are all going to cancel out. Excuse me, the components of those electric fields that are perpendicular to the x-axis are going to cancel out. You can pick any pair of those and they will cancel out in the direction that's perpendicular to the x-axis, but they will add in the direction that is parallel to the x-axis. So to get this electric field here, this yellow dot in the middle is supposed to be a vector pointing right out at you, which is the electric field, assuming these are all positive charges. So that would be the net electric field. Well, now let's go ahead and change this picture up just a little bit. Let's go ahead and make it, instead of a bunch of individual charges like that, let's make it, gosh, I worked so hard on my animation and a lot of them aren't working. I don't know what I did wrong. Well, it was working when I practiced. All right, so let's replace all these individual Q1s with a ring of charge that has a ring that has a charge Q that's equally spread out. It's a conductor, so the charge is spread out all around it. Quick reminder, by the way, I know we talked about this very briefly, but remember, these are point charges. So even though I'm drawing them as big balls, they are not really. They're just little tiny dots there. They have no dimension at all. And the same thing is true for this ring of charge. This ring, even though I'm drawing it as a wide blue ring, it's not wide, and in fact, it has no finite width at all. It's just an infinitesimally thin line that goes around in the circle along in the YZ plane perpendicular to the x-axis. Well, now every point there on that axis has a little bit of charge with it, and that little bit of charge is going to make a little bit of electric field. But for a little bit of charge, like would be in this little strip right here, there's also a little bit of charge in the strip right here on the point opposite to it. Well, what does that mean? That means that the components of the electric field that are perpendicular to the x-axis are going to cancel out. The only ones that are going to add up are along the x-axis. So we're just going to ignore the perpendicular component for now. Well, now all we need to do is the exact same thing we did before. What did we do? We said we know that some charge here is going to contribute a bit to the electric field that is K Q1 over R squared in the R hat direction. All right, so let's go ahead and think about what that little bit of charge is. Well, if the whole charge is Q and the length of this circle is 2 pi a, then each little tiny length right here has a charge on it that is lambda. So it's a charge density, which is lambda, which is equal to Q divided by 2 pi a. Okay, then we can then define a dq that is the amount of charge that's in just this little strip right here, this infinitesimally thin strip, we can define that dq as being equal to lambda times dl, where dl is just some tiny little length of this circle. Well, what does that mean? It means the electric field, now this is the exact same expression we had before. The electric field is equal to k times a charge divided by the distance squared, and what's the x component? Cosine theta x hat. Okay, so we know that the net contribution from this little bit right here, this is what that net contribution is going to be. So now all we need to do is take all these little tiny slices of charge and add them up. But as you guys know, when we're adding these infinitesimal things, we use the tools of calculus, and what we're going to do is we're going to integrate around this circle. So when we integrate, this is, I don't know why we did that, but there we go. Okay, when we integrate, this is what we're doing. We're integrating both sides. We're starting from nothing, so we haven't done any integral, we haven't added up any charges yet. So we're starting from 0, and we're going to add up all the charges until we get to some e total right here. So the integral on the left goes from 0 to e total, and the integral on the right goes from some point 0 to some point which is the end of where all the charges are. And then, so what are we integrating there? We're integrating this dq, which is lambda times dl. So what we need to do is we're going to be going from some starting point, which we're just going to call our 0 point, and we're going to integrate until we get to an ending point, which will include all the charges, and then we're done. So now it's just a matter of looking through and deciding what all these terms are. So we have, okay, so we know that on the left, the integral there just turns into e total. That's fine. And on the right, nothing there depended upon dl except for dl itself. So we can pull everything else out of the integral, which is what we did. Now, let's take a look. Oh, I'm sorry. Now, what is the limit on that integral? Well, the limit is we're going to start at 0. I'm just going to go ahead and say it's here because it doesn't really matter. Let's just say we started here, and we're going to integrate all the way around this circle. Well, what is the length? What's the perimeter of that? It's 2 pi a. So that's what we're going to integrate around. So that's our those are limits for our integral here, which means that we just end up with 2 pi a. And we should have, let's go back one more step there. Okay, so now we're done. We've done our integral. We know what the total field is. But now we have to say, now let's look at this and see if we can't make this a little bit simpler. So now we're going to take this same picture. Remember, right now we're looking down the x-axis at the yz plane. Now we're going to turn and look at this sideways. When we look at it sideways, this is just a cross-section through that ring right here. This is the equation we just calculated from the previous page, and this is the geometry we have, and this we know is going to be our E total. Remember, if this was negative charge, it would just put a negative sign on everything, and it would go back this way. So what we're going to do now is we're just going to look at this equation here and see if we can't simplify it. Well, first of all, let's look at that r. What is the r? It is a squared, this distance here, plus x squared, this distance here. I'm sorry, that's what r squared is. So we'll replace that, a squared plus x squared. We also know lambda was q, the total q, divided by 2 pi a. That's just the charge density, and you can go back and look at how we arrived at that if you like. Now let's take a look at what this cosine theta term is. Cosine theta is just, there we go. So cosine theta is a over r. But what's r? R is the square root of a squared plus x squared. So this x over a squared plus x squared, x over the square root of a squared plus x squared is cosine theta. So now we have that. Now it's we're going to just do a tiny little bit of algebra and cancel a couple things out there, and we end up with this expression. The total electric field is kqx over the the sum of a squared plus x squared, that quantity to the 3/2. And what direction is it in? It's in the x hat. And you can notice, just look at this equation here. If q is positive, what direction is E? It is in the positive x direction. If q is negative, What direction is E? It's in the negative x direction. You don't need to think about it because you've already done all your thinking with your drawing and your setting up of the problem originally. So you don't need to go back. You don't have an additional source of error there as long as you're consistent with everything that you write. Okay, take a look at example 21.9 in the book, and we will be working out some problems along these lines in class. See you.